Okay, hello. So welcome back to our chemistry problem solving session. So this is kind of a part two to the last one. So we're gonna just be continuing solving these problems and going through all of them. Okay, so let's start with number 25. So we're told that we have a sample of a diprotic acid. So that means it's of the form H2A, where this is the anion. So if we have this diprotic acid, then we can write out its neutralization reaction. So let's write that out. So we add NaOH to it, so NaOH, and that's going to form some water, which is obviously liquid, and then some salt, Na2A. And then we have to balance this, so a 2 goes here, and then a 2 goes here. Then, yep, it should be balanced. All right, so now we can find the moles of H2A, this diprotic acid that we don't know yet. So let's start out with what we have. So convert milliliters into liters, and we get 0.1375 liters. Multiply that by the molarity, 0.750 moles per liter. And then for every, notice that this is moles of solute per liters of solution. So this is in NaOH. So notice how for every 2 moles of NaOH, we have 1 mole of H2A. So now we have our answer in moles H2A. So if we calculate that, we should get 0.0516 moles of H2A. And then from here, we can find the molar mass just by dividing how many grams of it we have by the number of moles. So we do 6.50 grams per 0.0516 moles, and we get around 126 grams per mole to 3 sig figs. All right. Now for number 26. Okay, so citric acid has this molecular formula, and we're told we have a 0.250 gram sample of it. Okay, so let's start with what we know. We know we have 0.250 grams of C6H8O7, which is citric acid, and then we can convert that into moles by just dividing by its molar mass, which we can find. So its molar mass is going to be 192.12 grams. So yeah, we can go ahead and cancel the units, and we should get around 1.30 times 10 to the minus 3 moles of C6H8O7. And then we can also write out its what's it called? It's neutralization reaction. So let's call H sub XA, we'll call this citric acid, where X is the number of acidic hydrogens. So that means its balanced reaction is going to be HXA plus OH minus forms water and the anion. If we balance that, we would need X here and then another X here. All right, so to find the moles of OH minus reacted, we take this many, we can convert 37.2 milliliters into liters, so that's 0.0372 liters. And then we have the molarity, so it's going to be 0.105 moles of OH minus per each liter, because there's a 1-to-1 ratio. And if we multiply that out, we should get 3.91 times 10 to the minus 3 moles of OH minus. So then we can find this X here just by doing this. It's going to be moles of OH minus divided by moles of citric acid. So we already found the moles of citric acid at the top, and then we can use this value too. So we just do 3.91 times 10 to the minus 3 and divide it by 1.30 times 10 to the minus 3. This is going to cancel, so we just get around 3.01 as our x, so that's around 3. So then that means the general acid formula for citric acid should be H3 A, where A is the anions, because this pretty much means that citric acid has 3 acidic hydrogens, as opposed to like all of them being acidic. All right, so that's that one. For number 27, let's write out this reaction. So it's lead 2 nitrate, and then what was the concentration of the original? Lead nitrate. Okay, so we're told that we add an excess of concentrated sodium chloride. So let's try writing out the net ionic equation. So, it's going to be so it's lead nitrate and then sodium chloride. So whatever doesn't dissolve out forms the solid. So that's what's going to be left over is Pb2 plus and then Cl minus, which form the solid PbCl2. And there's going to be a 2 there if we balance it. Okay, so that means we can go ahead and convert into moles of ions. So we have the solid PbCl2 has a mass of 3.407 grams. Let's convert that into moles PbCl2. It's going to be 278.1 grams from its molar mass. Now we can use this net ionic equation to find our molar ratio. So in every 1 mole of PbCl2, there's also 1 mole of Pb2 plus, ions. So that's going to be, we cancel everything. We get 0.012225 moles Pb2 plus. Okay. And now we can go ahead and find the concentration. So we know we have 2 milliliters of this solution. So let's find the molarity. So it's going to just be moles over liters. This many moles divided by, so 2 milliliters is the same as 2 times 10 to the minus 3 liters. So that's going to give us 6.13 molar Pb2 plus solution. So since the ratio is the same, it's going to be the same as just 6.13 molar Pb NO32 solution. So this is also this concentration in the 80 milliliters. So that means the original concentration is going to be, first we have to find the moles of Pb NO32 within this solution, and then divide by the original volume, which was this many liters. It's going to be 0.1 liters. All right, so first we'll convert this to moles. So how do we do that? We go ahead and multiply by the volume, which was 80 milliliters or 0.08 liters. So this is in moles, and then we divide by the original volume, which was 100 milliliters or 0.1 liters. And then we get 4.90 molar PbNO32 solution. Okay, so this one, all right, so we have monoprotic acids HA and HB. And Okay, so we titrate with NaOH. So if we think about it, the balanced equations for either HA or HB with NaOH are going to be the same. So let's just do it for HA first. So HA, NaOH, is going to form NaA and water. So to find the concentration of HA, we were given 87.3 milliliters of this molar solution. So it's going to be 0.0873 liters times the molarity. So that's going to give us, okay, so it's going to give us something moles and moles HA. We can also oh my bad, this should be NaOH. And then we want to convert to moles HA. How do we do that? By using the equation we just wrote. So it's a one-to-one relationship. So it's going to be 0.007909 moles of HA. All right, and then we can find the molarity of this by dividing this this mole by the 43.5 milliliters, or we should convert to liters first. So it's going to be 0. Oh, 1 second. Okay, so then from this many moles, we go ahead and find the molarity of HA. So 0.007909 moles HA, and we go ahead and divide by this many liters, which gives us 0.182 molar HA. To 3 sig figs, and then so when we're talking about the titration of this acid mixture, so we're talking about the reaction of NaOH with both of these acids. So let's find out the number of moles of HA in the acid in like the total mixture. So that's going to be let's see, yeah, we have 37.2 . Let's convert that to liters, 0.0372 liters times what we just found. So it's better to use the unrounded value. So I'm going to just use that here. 18248 moles HA per liter. And that's 0.006767639. Okay, 67639. All right, so now we found that. So what we need to do now is find the volume of NaOH needed to titrate this amount of HA. So how do we do that? We just use the molar ratios and the given molarity of NaOH. So let's take this value one more time. So for every 1 mole of NaOH, there's 1 mole of HA. And then divide by the using the molarity, we can convert into liters, moles, NaOH. So that's just the molarity of NaOH. And then we can convert into milliliters since, everything is in milliliters in this case. So for 1 milliliter. So now we have around 74.656 milliliters NaOH. All right, so the volume in milliliters of NaOH needed to titrate HB is just going to be the total volume minus the volume needed to titrate HA. And we've already found the total. We've already found these values. So it's going to be, if we substitute what's given, so that's going to be 96.4 milliliters minus what we just found, 4.6565 milliliters, which gives us around 21.7435 milliliters of NaOH. All right, so now we do pretty much the same thing except with moles of HB. Well, not really the same thing. I'm gonna go ahead and make this smaller. So now for moles HB, so we've just found, right, the milliliters of NaOH needed to titrate HB, so it's going to be 21.7435 milliliters. So we can, go ahead and convert this to liters again for convenience. That's 0.0217. I'll leave it at that. And we have 0.0906 moles of NaOH per liter. And again, it's the same ratio because, it's the same even with HB and NAB. So it's 1 mole HB, 1 mole NaOH. We do the calculation, we get 0.0019 moles HB. All right, and then finally we can go ahead and take the volume HB. We know that volume HB plus volume HA is going to give us the total volume, or just, the volume of the mixture. So if we have this, then we can easily find this by subtracting from the mixture volume, the volume of HA. So the volume of HB is going to be volume mixture minus volume HA. So volume of mixture, the final volume is 15 milliliters. So it's 15 milliliters minus the volume of HA, which we found, which was given to be 37.2 milliliters. So that's the difference is 12.8 milliliters. And then finally from here we can find the molarity of the HB solution as well. I don't know if yeah, okay, so I forgot to bold this. So this was the molarity of the HA mixture. And we were just finding the molarity of the HB mixture by taking the moles and dividing by the volume, which is 12.8 milliliters or 0.0128 liters. That gives us around 0.154 molar HB solution to 3 sig figs. So there's that one. Okay, so for number 29. All right, so what's the concentration of the HNO3 solution? Let's write out the chemical equation. Okay, so so let's see, how much total do we need? Okay, so 20 plus 3.22 gives us 23.22 milliliters of NaOH. So that's how much NaOH it took to titrate a total of 50 plus 30, so a total of 80 milliliters of acid. All right, so let's find the moles of, so from the milliliters NaOH, we can find moles NaOH. From moles NaOH, we can find moles HNO3. And then from moles HNO3, we can go ahead and find the concentration of the HNO3 solution. So let's go ahead and do that. I'm going to start on the left end because it's going to be pretty long, but it's going to start out like this. So wait, let's first convert this to liters. So 23.22 is 0.02322 liters. And then convert that into moles by using the molarity given, 0.0502 moles NaOH per liter. And then for every 1 mole of NaOH, we have 1 mole of HNO3. And then we know that, so then we have moles HNO3, so let's first find that. It's going to give us 0.0011656 moles HNO3. All right, so we can go ahead and find the molarity or the concentration by dividing by the total volume, which was 80 liters, or sorry, 80 milliliters, or 0.080 liters. So that's just going to give us 0.0146 molar HNO3 solution. Okay, so that's it for part A, and then for part B, how many moles of NaOH were in excess after the first addition? All right, so to know how much was in excess, we need to find the moles of acid and base that were present initially, right? So let's find moles NaOH. So that's going to be, so we had 20 milliliters. Let's convert that into liters, 0.00200 liters of 0.0502 molar solution. So that's just 1.004 times 10 to the minus 3 moles NaOH. And then moles HNO3 is just, we had 50 milliliters or 0.05 liters. Oh, maybe I need another. Okay. So that's just So we already found the concentration of HNO3 from part A, so we're going to go and use that. I'm going to use the unrounded value, moles. Oh wait, that should be moles, and then moles per liter. So that gives us 7.28, oh boy, 275 times 10 to the minus 4 moles HNO3. So then, so this pretty much tells us that the number of moles needed to titrate this many moles of HNO3 is just, the same amount. So this many moles of the same number of moles of NaOH. So that means the excess is just going to be the moles added minus the moles required for the reaction. So the moles required is just going to, match this. It's going to be 7.28. But the amount present was 1.004 times 10 to the minus 3. So we just find the difference. It's just this minus this. So yeah, I just find the difference. We should get around 2.8 times 10 to the minus 4 moles NaOH. All right, and then for number 30, so there's this unknown alkali metal, carbonate, and then we dissolve it in water, and this many okay. This many milliliters of this are required. So we're trying to find the name and formula of the unknown compound. So let's consider the reaction. It's going to be M2 CO3. This is this unknown metal carbonate plus CaCl2. And what do we form? We form CaCO3, which is, it's not insoluble. It's insoluble. And then we also have MCl. Okay. So the reason I knew all this, like the formula and the structure and everything, was because it tells us it's an alkali metal carbonate, so it's, group 1. So yeah, since the alkali metal M forms a +1 ion, carbonate is a -2 ion, the formula is going to be M2CO3 for its balance. So now we can find the, let's start with what we know. We have 0.03110 liters of this 0.350 molar CaCl2 solution. And from here, we can go ahead and convert into moles of M2CO3. So that's going to give us 0.010885. All right, and we can go ahead and find the molar mass of M2CO3 since we're given, it's 1.50 grams and we have the moles, so we can go ahead and divide 1.50 by this number of moles that we just found. And that's going to give us around 137.804 grams per mole. So this is the molar mass of M2CO3. And we can go ahead and isolate the mass of M2 because we already know the mass of CO3, right? So we can, I find the molar mass of M2 So from this total, we go ahead and subtract the mass of CO3, and we're left with the mass of M2. 7.804 minus the molar mass of CO3, which is around 60.01, and we get 77.79 grams per mole. So we can go ahead and find the molar mass of just plain M by dividing this by 2. So we get around 38.895, which is around 38.9 grams per mole. So we go and look at the periodic table. What is it, really close to? It's really close to potassium, the alkali metal potassium. So the formula is going to be K2CO3. Its name is potassium carbonate. And yeah, we're done. All right, and now for number 30. For number 31. So, all right, so we're trying to find out what this compound is. So for now, let's go ahead and call it MCl2. It's going to form ions with a plus 2 charge. So to that we add AgNO3, and we form the insoluble AgCl and then some other product, MnO3 too. So we go and balance it. Since the metal is a +2 ion and chloride is a -1 ion, the formula is MCl2, and similarly this is MnO3 too. All right, so now from what we know, which we have 0.02240 liters, converting from milliliters to liters, of this 0.515 molar AgNO3 solution. And then from here, we can go ahead and use this relationship to convert to moles of MCl2. So we know that for every 2 moles of AgNO3, there's 1 mole of MCl2. We'll cancel all the units. Oops. Okay, and then from here, we go ahead and get 0.005768 moles of MCl2. So we can find the molar mass of MCl2 in the same way that we did in the previous problem by dividing the grams by the moles. So it's 0.750 grams over 0.005768 moles. It's going to give us around 130.0277 grams per mole. So if this is the molar mass of MCl2, we can, find the molar mass of M just by subtracting the mass of Cl2. So it's just going to be 100 this minus molar mass of Cl2, which is 70.90. So that's going to give us around 59.1 if we round to 3 sig figs. So that's closest to that of nickel. This molar mass is closest to that of nickel, so the compound is NiCl2. 1 second, I'm going to go ahead and get my pencil charged. Okay, so I left off, yeah, so I left off with the name. So NiCl2, that's the compound, and its name is nickel 2 chloride. Okay, so that's that one. It's really similar to the previous one. Now for number 32, so we have AgNO3. Okay, so let's try writing out the equation. So AgNO3 plus Cl minus going to react to form AgCl, which is insoluble, and NO3 minus. All right, and now we can go ahead and find, so let's start with what we do, what we have. 0.05363 liters of this molar solution. And then from here, we can go ahead and convert to moles. So this is AgNO3. So for every 1 mole of AgNO3, there's 1 mole of Cl minus. And then in 1 mole of Cl minus, there's around 34.45 grams Cl. So that just Cl, and that gives us around 56465 grams of Cl minus. So then we can go ahead and, so to find the mass percent of Cl minus, we have to find first the mass of the seawater sample, right? So the mass percent Cl minus is going to be the mass Cl minus divided by the mass, of the sample. So let's now find the mass of the sample. We had 25 milliliters of seawater, and we're given its density, so we can go ahead and convert into grams. 25 milliliters, 1.024 grams per every milliliter. It's going to give us around 25.60 grams. So now we have all the relevant information. Of course, we multiply by 100%. So that gives us 0.56465 divided by 25.60 times 100%. It's going to give us 2.206% Cl minus to 4 sig figs. All right, let's do number 33. Okay, let's write out the relevant equations. So first, let's write out this one, NaOH plus oxalic acid, which is H2C2O4. So this is aqueous. Form Na2C2O4 and water. It's going to be 2 there. So this is aqueous, this is a liquid. Oh wait, I wrote that already. And then we also have, oh yeah, and benzoic acid. So it's NaOH plus HC7H5O2 form NaC7H5O2 and water. And then lastly, we have just the excess NaOH being titrated with HCl. So that's just NaOH plus HCl form NaCl and water. All right, so let's go ahead and keep things in moles and we can convert to millimoles. So in the start, beginning millimoles of NaOH are, so we have 100 milliliters of this molar. So it's going to be just moles per, well, yeah, if we just multiply by molar, it's going to give us 10 millimoles. And then the excess of NaOH is what we have at the very end, which is 20 times this many moles. It's going to give us this many millimoles. All right, so now that means that the amount reacted is just this difference, which is 6.00 millimoles. Oh, one extra zero. Okay. So now we have this many millimoles of NaOH that were reacted. So now let's do some algebra. So let's let X be the mass of oxalic acid, and then Y be the mass of benzoic acid. So if we do that, then we can write out some equations. So we know that X plus Y are going to add up to the total mass of the sample, which is 0.3471. And then we can write out their molar relationship as well. So, it's easy to convert from millimoles to moles. We just multiply by 10 to the minus 3. So this is just the same as this many moles. So let's also write out their molar relationship. So let's convert this into moles by dividing by the molar mass, which is 90.04. Oh, and we also should multiply by 2 since there are 2 H's. So let's multiply that by 2. And then for Y, we go ahead and just divide by 122.12. And this adds up to 6.00 times 10 to the minus 3. All right, and we can go ahead and use substitution or whatever method. So Y is going to just be 0.3471 minus X. Substitute that here, and then we go and solve for X. We get that X is around 0.2252 grams. All right, and then, yeah, we're pretty much done. Just to find, because we already found the mass of the oxalic acid, so we can go ahead and substitute back to find Y. So Y is just going to be that minus that. And then we go ahead and divide whatever we get for Y by the total mass of the sample. So we just do Y, whatever Y is, and divide by 0.3471. So I don't have the numbers right now, but you can calculate that using this. And now for number 34. Okay, so we have neutralization reactions again, so let's go ahead and write them out. I'm going to write out the balanced equations. 3HNO3 plus AlOH3 AlNO3 3 plus 3H2O. And then the same for MgOH2, the neutralization reaction. 1 second, I'm gonna go ahead and charge my Apple Pencil one more time. Okay, starting from where I left off, we have plus 2H2O. All right, and then we can go ahead and find moles HNO3 by using the information given. So converting milliliters into liters gives us 0.01730. And then if it's just 1 molar, it's going to be the same number of moles. 0.0173 moles HNO3. All right, so let's do a little more algebra. So let's go ahead and let X be the mass of AlOH3. So we can find the mass percent later, and then let's let Y be the mass of MgOH2. So that means, Y is just going to be equal to, because since X plus Y add up to 0.4826, Y is just 0.4826 minus X. So let's just write it like that, and X. So the number of moles required to titrate MgOH2 is going to be it's going to be 0.4826 minus X, so this many grams MgOH2 times, so we're given the molar mass. 1 mole is 78 grams. And then we know the relationship between it and moles HNO3, so for every 2 moles HNO3, it's 1 mole MgOH2. And of course, this is all in, MgOH2 and whatnot. So let's go ahead and cancel everything. And we get this expression. Okay, so then we go ahead and solve for, then we go ahead and...
Wait, isn't it 58.33, not 78?
Oh, wait, 1 second. Sorry, yeah, I was doing the wrong... Okay, so this part is for AlO3H. I'm gonna go and put this on the bottom. Or, yeah, I'll just erase this for now. Yeah, sorry about that. I was doing the MgOH2 part first, so, or the Al part first. So let's actually do the Al part first. AlOH3. So we start out with X grams of AlOH3, and then we convert to moles by using the molar mass. OH3, which is, in this case, it's 78 grams. And then we go ahead and use the relationship. So 1 mole of this is the same as 3 moles of HNO3. So that gives us this expression, 0.038462x. And then for the next part, the number of moles HNO3 needed to titrate MgOH2 is going to be 0.4826 4826 minus X grams MgOH2 times 1 mole is 58.33 grams, and then 1 mole MgOH2 is the same as 2 moles of HNO3. So that gives us this expression. If we simplify everything, we get 0.016547 minus 0.03428x. Or 288x. And then we know that the moles HNO3 needed to titrate the sample is just going to be the sum, and it's going to add up to this many moles. So that's because it's 1 molar. So yes, if we already converted earlier, we found this many moles. So we go ahead and set 0.0173 equal to the sum of this expression and this expression. All right, and then from here we can go ahead and solve for x, which we first defined as the mass of AlOH3. And then we can find the mass percent. So x is going to be around 0.18040 grams AlOH3, and then from there we can go ahead and divide this by mass of the sample, which was 0.4826, multiply by 100%, and that gives us around 37.38%. And that's the mass percent. And now for number 35. Okay, so if this was needed to reach the endpoint, what is the mass percent of H2O2 in the sample? Okay. So we have to take a couple of steps to get there. So let's start out with what we have. So this many milliliters is the same as 0.0432 liters. Convert that into moles by multiplying by the molarity, and this is going to also be the same as moles MnO4 minus. So for every liter, and that's going to give us something in moles MnO4 minus. From there, we can go ahead and convert into moles H2O2 by using the molar ratio given in the equation, H2O2. So this is given here. And then from here, we can find the mass by multiplying by the molar mass. So for every 1 mole, there are around 34.02 grams given in the problem. So this gives us 0.386 grams of H2O2. So out of the total of 14.8 times 100%, so the mass percent is going to be 2.61% H2O2. And then for part B, what is the reducing agent? We just have to look at, what. So the reducing agent is oxidized, so we need to look at what's being oxidized. Let's look at the numbers, the oxidation numbers for each parts. So for Mn, it's going to be +7. Oxygen is going to be -2. H2O2. So H2O2 is a special case in which O is actually -1. So yeah, so I think you guys know how to, like, yeah, you guys know how to write oxidation numbers, so I'm just gonna go ahead and write them on top of the element. So this is -1 and this is +1. Oh, I think this is a typo. I don't think that should be there. Yeah, it doesn't make sense. So it's +1 for H, and O2 is 0. This is +2, -2, +1. All right, let's see what is being oxidized. So you can notice how, so the total oxidation number, I guess. So let's look at what is being oxidized. So which one is increasing pretty much. So you can see that for oxygen, it's increasing from -1 here to 0 here, and it's therefore being oxidized. Meanwhile, for Mn, it's decreasing from +7 to +2. So that means this is being reduced. Therefore, the reducing agent, which is the one being oxidized, is actually H2O2. So the reducing agent is H2O2. For number 36, okay, so we have this many milliliters, which is the same as 0.03546 liters. Convert that into moles of dichromate, I think. Yeah. 0.5961 moles per liter. And that's going to give us around 0.00211138 moles, 0.2072 minus. And then from here, we can go ahead and, I should have done this in one step. I'm going to do it in one step. So for every 2 moles, oh my gosh, for every 2 moles of dichromate, Cr2O72 minus, we have 1 mole of this CH2, oh my god, C2H5OH. And then from here we can go into grams. 1 mole of C2H5OH. Molar mass we can find is, or it's given, it's 46.07 grams. That gives us 0.0486 and then 4 grams of C2H5OH. So we can go ahead and find the mass percent just by dividing this number by the initial mass of the sample, which was 28 grams, times 100%. This will cancel and we'll get 0.1739% of alcohol. Okay, and then for number 37, so a mixture of this with a mass is heated to produce O2. After heating the mass, a residue was this, assuming all, okay, so this is pretty much telling us that KClO3, which is a solid, so if we, heat it up, it's going to decompose into KCl, which is solid, and O2, which is a gas. So balancing it gives us that. So the mass of O2 produced is pretty much, okay, I'm gonna be right back. I'll charge it one more time. Okay, so we have that the mass in grams of O2 produced is the difference of the mass of the mixture and the mass of the residue. So pretty much if we add this O2 produced to the residue, we're going to get the mass of the mixture. So if we go ahead and plug in all the values, we should get the mass of O2 produced. So 0.950 grams minus 0.700 is going to give us 0.250 grams of O2. All right, and now from here we can go ahead and convert using this equation. So we have 0.250 grams O2. Let's convert into moles. 1 mole of O2 is 32 grams. And then for every 3 moles of O2, we have 2 moles of KClO3. And every 1 mole of KClO3, there are 122.55 grams from its molar mass. So that is going to give us 0.63828 grams KClO3. All right, cool. And now from here, we can find the mass percent just by dividing this value by the original mass of the sample, which was 0.950. It's supposed to be an 8, and that gives us, and then, of course, times 100%. And that gives us 67.2% as the mass percent. All right, cool. And now for number 38, how many? Okay, so there's still a couple left. For number 38, it's kind of a similar problem where we heat CaCO3. We heat it up to produce CaO and CO2 gas. So, in the same way, the mass CO2 produced is going to be the mass of the mixture minus the mass of the remaining solid. So it's the same as 0.693 minus 0.508, which is 0.185 grams of CO2. And now we pretty much do the same exact thing we did earlier. So this is already balanced. It's 0.185 grams CO2. Convert to moles. And then convert moles CO2 to moles CaCO3. And then convert again to grams. And we get 0.420737 grams CaCO3. And from here we can divide by the mass of the sample, which was 0.693, and multiply by 100%, we get 60.7% CaCO3. So it's very, very similar to the previous problem. And then we're done. And now for number 39. Okay, so we know that solid magnesium is reacting with HCl solution, MgCl2, and H2 gas. So this is the equation. All right, let's try to find, let's first find how much HCl is being added. So 0.75 moles per liters. Okay, and then that's the same as just, okay, so it's already in liters, which is handy. Whoops, sorry, I think I was muted. So it's 0.0750 moles of HCl. So the moles of HCl that react with Mg are pretty much the mole. So if this is what we have at the beginning, and if 0.125 is what we have at the end, the amount reacted is just their difference. So yeah, I hope that makes sense. So it's just this minus 0.125. And this difference is going to give us moles HCl reacting with Mg. So that difference ends up being 0.0625 moles of HCl. Okay, so then from here we can go ahead and use our molar ratios. So 1 mole of Mg is 2 moles HCl. And we can convert into grams grams of Mg by using the molar mass, 24.31 grams. And that's going to give us 0.75986875 grams Mg. Okay, and then from here we can go ahead and divide by the original mass of the sample to find the mass percent. So divide by 1.32, multiply by 100%, and we get around 57.6% magnesium. Okay. And now for number 40. So we're given these solutions and we need to determine their concentrations. Alrighty. Okay, so let's write down these two chemical equations that are relevant to this problem. So the first one is this: NaOH plus HCl and then the next one is NaOH plus H2SO4. So the states are exactly the same as above. I'm going to have to balance this one, so a 2 goes here and a 2 goes here. So let's go ahead and find the NaOH concentration from the reaction of NaOH with H2SO4. So we had 0.0500 liters of 0.0782 moles per liter. And then from here we can find the moles of, this is H2SO4, so we can find the moles of NaOH using the equation we just wrote. So it's 2 moles of NaOH. And that gives us 0.00782 moles NaOH. Okay, cool. And then from here, we can go ahead and find the molarity because we know that we had 18.4 milliliters to begin with, so it's 0.00782 divided by moles divided by 0.0184 liters. And that gives us 0.425 molar NaOH. So we found the concentration of NaOH first of all. So that's cool. And then from we can use this along with the reaction of HCl with NaOH to determine the concentration of HCl. So let's start with what we have. We know that we had 27.5 milliliters of NaOH, but we didn't know the concentration, but now we do. So 0.0275 liters times the concentration of NaOH. Sorry, that's supposed to be moles, and then per liters. And we use the molar ratio, 1 mole of NaOH for every 1 mole of HCl. And that's going to give us 0.0116875 moles of HCl. From here, we can find the molarity just by dividing by the volume. So it's going to give us, it's going to be this divided by 0.1 liters, which is just 0.117 molar HCl. So there's that one. And now for number, okay, for number 41, yeah, this is a lot. Predict the products and write a balanced equation for each of the following redox reactions. All right, so for the first one, the products are going to be, the product is going to be SRBr2, which is a solid. For the second one, we're heating up Ag2O. So that's going to give us Ag plus O2 gas. So 2, 4. And then for part C, so I'm just going to write out the answers for now. So part C, it's going to give us MgCl2 H2. For part D, oops, this is for part D, my bad. And then for part C, MnNO3 plus Cu. And then for part E, Cl2. For part F, COCl2 plus SN. And then for part G, it's going to give us NH3, 2NH3. And the 3 goes there. Okay, and then for part H2NaCl, and this 2 goes here, plus 3O2. And then for part I, for part J, so I'm just writing the answers here for now, but later I'll prepare a different meeting where I can go over all of these in more detail. I'm gonna just, yeah, do the same for this, or this one isn't too bad, because we just have to predict the products and write a balanced equation. Okay. So for A, it's going to just be plus I2 2 CSI. For part B, aluminum, and then manganese sulfate, Al2SO4 3, and then 3Mn. For part C, it says write a balanced net ionic equation, so keep the solid a solid, and then split apart into the ions. Split this apart into ions as well. 2Al3 plus. And 3SO4 2 minus. And 3Mn stays solid. So we can cancel and I think that's it for part D. These are both gases. So we do that, and then SO3, which is also a gas. So 2 goes there, 2 goes there. For part E, we have pentane and oxygen. So that's going to form CO2 and water. So that's 6 and then 5, yeah. Phosphorus trichloride plus chlorine, it's an L, chlorine gas, PCl5, which is solid, zinc, hydrobromic acid, ZnBr2, oh, it's aqueous, and hydrogen gas, and then 2 goes there. Potassium iodide plus Br2, which is liquid, form KBr, and I2, which is a solid, so 2 goes here and 2 goes here. And then for part I, write a balanced net ionic equation. All right, and then what's left is the net ionic equation. All right, and I think that's all the problems. So I will in a separate session I will go and prepare like all the solution, or I guess all the processes and everything for these ones. But for now, I think that's all I have for today. So thank you so much for coming, and yeah, if you have any other questions, then you can maybe ask them next week or ask them now, and I'll see if I can answer them. But yeah, thank you for coming.